This is the Chemistry 101 third hour exam review. Number 11, cis-trans isomers. For cis-trans isomers possibly existing, you have to have differing groups on both of your carbons. Since this is different than that, the possibility exists. Since this is different than that, you can have cis-trans isomers. Here, these R groups, R and R prime, are on the same side. This is cis. The R and the R prime are not on the same side. This is a trans relationship. Number one, is there cis-trans isomers possible if we label the two carbons involved in the double bond 1 and 2? Attached to this carbon is a CH3 and a hydrogen. Attached to the carbon labeled 2, we have 2 hydrogens. Since these groups are identical to one another, there can be no cis-trans isomerism possible because these things are the same things. Whatever is attached to the carbon involved in the double bond have to be different on both carbons of the double bond for there to be cis-trans isomers. Number 2, again, labeling the double bonds, the carbons of the double bond 1 and 2. Attached to this carbon, carbon 1 of the double bond, we have a CH3 and a hydrogen. Attached to carbon 2 of the double bond, we have a hydrogen and a CH2, CH3. Are both the things attached to this carbon of the double bond different? Yes. Are both the things attached to this carbon of this double bond different? Yes. Therefore, we can have cis-trans isomers. This is the cis isomer. CH3 and the CH2, CH3 are on the same side of the double bond. If we flip and put the hydrogen here and the CH3 here, these are trans to one another. So compound 2 has cis-trans isomers possible. Number 3, again, double bond carbons labeled 1 and 2. Attached to C1, we've got a CH3 and a hydrogen. Attached to 2, we have a hydrogen and a CH3. Are the things that are attached to this carbon of the double bond different from one another? Yes. Potentially cis-trans isomers. What is attached to this carbon of the double bond? Are they cis-trans? Are they different from one another? Yes. Both the carbons attached to this double bond are different. Both the materials attached to that carbon of the double bond are different. We can have cis-trans isomers. So both 2 and 3 can have cis-trans isomers. Number 12. Which of the following is typical of a fatty acid? Fatty acids are long, linear hydrocarbon chains that usually have at least one cis double bond in them. So the best answer is number B for question 12. Question 13. What is the name of this specific kind of addition reaction shown? What are we doing to this double bond? We're adding the H and the X to it. What is the X? X can be a variable. It can represent either a chlorine or a bromine. So we're adding hydrogen to this carbon, to the second carbon, we're adding a halogen. So the best answer here for 13 is answer D, hydrohalogenation. Number 17, correct answer here should be E, because alcohols do not have lower boiling points than ethers, they have higher boiling points. So the correct answer here is E. Number 23, of these molecules, which are chiral? Chirality requires that we have a carbon atom bonded to 4 different things. since these are skeletal structures where lines meet, start, or end, we have carbons. Carbon, 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 lines meet carbon. We fill in, or we make the assumption that if you do not see a line, that carbon has all the hydrogens necessary. So this is a CH3, hydrogen, hydrogen, hydrogen. Carbon, hydrogen, hydrogen. Carbon, hydrogen, hydrogen. CH3, CH3. All those carbons have at least two things that are identical attached to them. Three hydrogens, two hydrogens, two hydrogens, two CH3 groups. This carbon is attached to the OH, the CH3, which is identical to this CH3 and that CH2. That carbon is not chiral because these two things are identical to one another. B, CH3, CH3, CH3 carbon, CH2. All these three CH3 groups are not chiral. They have identical things attached to them. This carbon has three identical things attached to it. That carbon has two identical things attached to it. So in B, there are no chiral carbons. In D, CH2, 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 carbon. The four CH2 ring carbons are all identical to one another. Two hydrogens. Carbon is bonded to four things. If two of them are identical, it cannot be bonded to four different things. So 1, 2, 3, 4, those carbons are not chiral. This carbon is bonded to a hydrogen and an OH, but it's also bonded to a CH2 and a CH2. Is there any other difference further down? Well, what's this carbon bonded to? A CH2. What is that carbon bonded to? A CH2. Well, what is this carbon bonded to? A CH2. What is this carbon bonded to? A CH2. So as we go around this ring, we come to no potential difference on any of those carbons. D is not chiral. Compound C is chiral. This carbon is attached to three hydrogens. That carbon is attached to two hydrogens. These carbons right here are attached to three hydrogens. This carbon is attached to two identical carbons. So all of these guys are not chiral, but this carbon is. It's attached to an oxygen, a hydrogen, a 2-carbon fragment, and a 3-carbon fragment. So that carbon is chiral, therefore molecule C is chiral. Number 31, the reaction of a carboxylic acid with an alcohol in the presence of an acid catalyst forms an ester. This is known as Fischer esterification. It tells you it forms an ester. Therefore, this is an esterification, a Fischer esterification type reaction. Number 32, clavulanic acid, structure shown below here. It's a molecule used in combination with other antibiotics to overcome antibiotic-resistant molecules. Which functional group is not contained in clavulanic acid? Carboxylic acid, lactone, beta-lactam, ether. Ether, carbon, oxygen, carbon. Carbon, oxygen, carbon. Ether. Let's move that down. Ether. Carbon, oxygen, carbon. We've got it. A carboxylic acid, C double bond O, OH. There's your carboxylic acid. A beta-lactam is a cyclic amide. An amide, C double bond O, N. C double bond O, N. That N cycles back around on itself to reconnect to the C double bond O. So a lactam is a cyclic amide. We have that. The only thing we do not have is a lactone. A lactone is a cyclic ester, where the carbon that is bonded to your singly bonded carbon, this carbon is bonded to the oxygen that's bonded to the carbon of the double bond. This cycles back on itself to a cyclic system. So we do not have a C double bond O oxygen bonded to another carbon group in a cycle. So we do not have a lactone in that molecule. So the answer here is B. Number 33. The pH of the aqueous environment in cells. Carboxylic acids exist primarily in their ionized form. It's an acid. What do acids do? They donate the H+. If we lost the H+, it becomes this dianionic species. Of the following, A, B, C, D, or E, shows us the correct form in which this carboxylic acid exists inside the cell. Well, it's an acid. It loses the hydrogens. It becomes the minus species. So the correct answer is A. We have both the carbonyls and the minus oxygens. C is not correct. It does have the ionized oxygens, but it does not have both carbonyls. Number 33. That was 32. Okay, so we've covered these, and the last one, 34. What was the name of Superman's home planet? Krypton, letter D. Hopefully this is helpful. If I didn't answer your exact question, please make an appointment to come to my office during my office hours. Thank you very much. Have a good break.